we're finally able to move from the OSPF concepts into the configuration. At least the basic configuration. Then we'll have to go back to the drawing board to the concepts again before we get more advanced. What our goals are in this section is going to be getting OSPF working, but more than that, to actually watch the OSPF process before our eyes so that we're able to see the concepts that we just saw and we just spoke about in the concepts part 1 and part 2 videos happen as the neighbors come up and negotiate. We'll then move into the router ID and router priority options, which influences the name of the router and its level of being elected, or its likelihood of being elected as a DR or BDR. And then finally, we'll get into a lot of clearing and verification of OSPF. And as usual, I think you've gotten the feel for the implementation videos. I'm going to keep this as real world as possible. So as we go through the clearing and verifying, we're going to be doing that the whole way through. So once we get a router running, we'll be doing debugs, we'll be doing show commands, we'll make sure everything's set up on that router, and then move to the next. So spliced all the way through will be the verification. Let's get going. Here's the topology that we're going to configure for OSPF. Now, I chose this topology because it'll let us see both types of networks, or both styles of networks that neighbors will negotiate across. You can see a point-to-point link here. Then we've got a nice LAN segment over here where we've got 3 routers on the same one. That'll also let me demonstrate where the DR, the BDR get elected, and you'll be able to see one that's neither of those router types. So let's get started. I'm going to start up here on router 1. Let me bring up the prompt. So router 1, I'll just glance back at the diagram. We've got 172.30.49.0 as one part of the process, and then 10.1.14.0/30 as the other part. Now, the OSPF configuration relies heavily on the wildcard mask. So I'm going to get into router 1, go into global config mode, and type in router OSPF, followed by a process ID. Now, the process ID can be any number that you want. It's not the same as the autonomous system number that we saw with EIGRP. It does not have to be the same on all routers. But with that being said, most of the time it is, because otherwise you have to remember the process ID on all the routers. I'll use 1. Now, once I get under the router process, I'm going to type in on here network, the network command, and then I'll do 172.30.49.0. Let's start off with that style, 49.0. 0.0.0.255 is the wildcard mask, which says I care about digits in the first 3 octets. I will enable OSPF on interface that start with those digits, but I don't care what's in the last octet, that 0 right there. Now, I could have also done this. Could have typed in 49.1. 0.0.0.0, which would do the same exact thing. Enable OSPF on just that interface, because we can see that router 1 has the .1 address of there, and the wildcard mask says everything is significant on there. Now, we have to follow that up with the area ID. At this point in the game, I want to set up all routers in the same area, and the first area that we create with OSPF is the backbone, area 0. So I'm going to go ahead and hit enter on that command, and we've started the OSPF process. It's now running on this router. If I go back and type in show IP OSPF interface, I'll see that I have now OSPF running. It's running for this address, the network address that I typed in. Area 0 is the area that it's put in, and I can see the hello and dead timers by default, because this is a broadcast network. So once every 10 seconds a hello is sent, a dead timer is once every 40 seconds. That verifies what we talked about in the concepts part 1 video just a few videos ago. Now what I want to do is I want to turn on a debug. I'm going to type in debug IP. Well, you know what? I'm not going to do that yet. The reason why is I don't have router 4 turned on for OSPF. I want you to see the process of neighbor negotiation, but since router 1 is the first router, let's just get it running. I'll do a show IP interface brief, and I can see my active interface right here is 10.1.14.1. So I'll go into router OSPF 1, network 10.1.14.1. Now that's a /30 or .252, so I could either type in a subnet mask. I could either type in this with the subnet mask of .3, because the wildcard mask is always 255s, a bunch of 255s minus your subnet mask. This is a .252 in decimal, and subtract that all out. That's 0.0.0.3. 3 for that network. Or I could just do it like I did before. That's my preferred, with all zeros and just focusing on that one interface. We'll do it this way just for grins. I'm going to also put that interface in area 0. So now when I do a show IP OSPF interface, I can see that OSPF is running on 2 interfaces, both with the same hello and dead timers, because only when we get into the non-broadcast multi-access world do we see the hello timer go up. So router 1 is done at this point. I can now jump over to router 4. But before I do, one more quick thing. I'm going to bring up the router 1 prompt again. Looking at the IP addresses that we have here on router 1, what do you think would be the router ID? Well, looking at that list, I can see that we've got the serial 0.4. That is an active interface. And remember, only active interfaces are part of the process. So these interfaces that are turned off, administratively down, don't even get a vote. I have this one right here, and I have this one right here that is part of the active process. And if you remember, the higher IP address becomes the router ID. Let's verify and see if we're right. So I'm going to type in show IP OSPF. And you can see that I have, sure enough, routing process OSPF1 with ID, that's the router ID, 172.30.49.1. So you can see that router 1's name to the OSPF process, how it identifies itself to the other routers, is going to be the highest IP address on any interface. We'll revisit that a little bit more as we configure router 4. So let's hop over to router 4. Moving a little more quickly, I'm going to go into router 4 and type in config T router OSPF1, and let me just do a quick show IP interface brief. And let's just let's get brave here. I'm going to type in network 172.30.50.0 0.0.0.255. Put that in area 0, and then I want to actually do a debug. I'm going to type in debug IP OSPF, and let's do a debug of the let's check out the adjacencies and the events so that we're able to see. I knew that would happen. So that we're able to see the adjacencies. And you can see right here, I received a packet from this router, just received another one, from something not on the same network. And the reason why is I actually have these two interfaces configured in the same switch. So quick way to fix that. Close your eyes real quick. And I'll hop over to the switch, go into interface fast Ethernet 0/1 and just do switchboard access VLAN 10. Let's throw it into a different VLAN. Just because even though logically this is the setup, they're actually all plugged in the same switch. And it was saying, hey, wait a sec, I see a router that's, not having the same subnet mask. They're part of a different network. So that was the complaints. Those complaints should go away. So let me clear this off. And let's hop over to router 4 again. Now, router 4, we've got show IP OSPF interface. We've got the OSPF running on Ethernet 0/0. And since the debug is on, I'm going to see every single time it sends a hello message. Now, notice the hellos are being sent to 224.0.0.5, which, if you remember from the Concepts 2 video, was the OSPF address for all routers. 224.0.0.6 is to the DR and the BDR. So let's continue on a little bit, but before I do, I keep having thoughts as I'm glancing at output. Look at this router, and you can see right there, when looking at the interface, the state is that it is the designated router. I am the DR, it says, because there's no other routers that I've communicated with on this interface. No, router 2 and router 3 aren't running yet, so I will be the DR for this whole segment, and router 1 would be the same for its Ethernet segment. Cool. So let's hop over here and watch the neighbor relationship. And we're going to get some flurry of messages here. And type in router OSPF1, and let's turn it on for network 10.1.14. Let me glance again. 10.1.14.2 is our IP address here. We use a wildcard mask of all zeros because it's easy. Area 0. Now watch the fireworks. I hit enter. As soon as I do that, it's going to send a hello message. Oh, this is such good stuff. Such good stuff. Hang on. Can I pause this? Let's freeze right here. I'm just going to hold my little scroll bar on the right so I don't scroll any further. What I can see here is that first off, you see the interface going up. Sorry, I'm trying to move my mouse while keeping the screen from scrolling. So interface goes up, sends a hello on the interface, right? Whoa. Right there it says, I'm building an LSA. an advertisement for area 0. Remember the terminology, a link state advertisement for that network. And I received a hello. Hey, this is great. I received a hello. Now, take a look at that. Wait a second. 172.30.49.1? That doesn't make sense. Well, hang on. I'm going to type in you all so that I can stop the debugs from coming through. Because how did it receive a hello from this interface? Hang on, let's get back to that and scroll up a little bit again to analyze these messages. It says right there, it received a hello from this person on serial 0/0.1. Aha. Are you thinking what I'm thinking? That's not the IP address it received a hello from. The IP address it received a hello from was 10.1.14.1. But that is the router ID. That is the name of the router that it received the hello from, which we saw on router 1. That's what it was elected. So notice right there, the state has moved into a two-way relationship. Think back to the phases that we went through when we were negotiating neighbor relationships. We went from down to init to two-way. I was trying to think of the other one is initializing, and that's what was happening right here. It didn't actually show init. But right there, we've established two-way, which means the hellos are okay. We've checked them out, and all the criteria match, so we can form a neighbor. So notice it says, I'm not waiting. I'm going to send a DBD, the Cliff Note summary, to my friend across the neighbor. And it says, and I'm going to send an immediate hello to make sure they're still there and we're still processing. Right there, it receives the DBD, the Cliff Note version of the database, and it says, hey, we are the first DBD. We are not slave. We are the master. Does this make sense? Do you see how valuable? I'm getting all excited here. Do you see how valuable it is for us to understand the concepts of OSPF? This is the whole neighbor negotiation process that we talked about in the OSPF Concepts Part 1. Slave and master, just saying that the master sends its DBD first. It says, I will send the first DBD because we are not the slave. I will receive the DBD because I'm the master, and then from there, they're going to send link state requests. You catch that? It's saying, hey, I've got a request. I don't know about this network. I don't know about that network. Now, we don't know the specifics of those packets because we're not doing that deep of a debug. We just know that we sent a link state request over to the neighbor. We also received one from our neighbor saying they needed some information about the network we were talking about. So we updated them. We said, here's the update. Here's the scoop, the LSU, if you remember that back to that packet, the LSU about the network that you're asking about. And it's continuing down. Received an update from that neighbor, so they were responding to our request. And by the time it's said and done, they exchange a few updates back and forth, and the neighbor relationship is then formed. From there on out, you can see that it's just hello, 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 hello. But hellos back and forth, maintaining that neighbor relationship. Now I jump back here on router 4. Let's do a show IP route first of all, because we can see that we have an OSPF route in the database or in the routing table saying 172.30.49.0. It has learned about this network up here behind router 1. And if I do a show IP OSPF neighbor, I can see that I have formed a neighbor relationship with this neighbor ID, aka router ID. The IP address that I'm reaching them on is this address. Notice that that address is the physical interface right there. Whoop, that's the wrong tool for that. Right here is the physical interface that we're looking at, but we're seeing that that is the neighbor ID right there. So you're able to correlate the name of the router with the physical interface with this command, what interface I'm going out to get them, and I would say the most beneficial one is the state. Full is what we want to reach. We want to move to that process of being a full neighbor. Now, you see a little dash right here because we don't have any other neighbors yet. But this dash is usually where it will say if it is a DR, if it is a BDR, or if it is a DR other, which means it's neither one of those. Now, when you're looking at this topology, this point-to-point network does not have a DR and BDR because remember, think back to the concepts part 2. I said the point-to-point neighbors don't form DR and BDR because there's only 2. It's point-to-point, so there's no point in doing that. So witty. Let's take a look at router 2 and router 3 now. Now, before I jump over to those configurations and get them set up, router 2 and router 3 will start negotiating with router 4 via their election ballots to try and become the DR and BDR. Now, of this crew, by default, now everything is at the default settings, who do you think will become the DR and who will become the BDR? Well, if you think about it, the router priority decides the election. But right now, all the router priorities are 1. They're all tied. So it's going to have to resort to the router ID, the name of the router, to break the tie. The higher the router ID is, the more likely you are to win the election. So in this case, router 4 will have a router ID of 172.30.50.4 because that's its highest IP address. Router 3 will be .2 or .3, and router 2 will be .2. So once all those are configured, router 4 should be the DR, router 3 should be the BDR, and router 2 should just be a router. So let's get them set up. I'm going to bring the prompt back up, jump over to router 3. These should go quick. I'm going to go into router OSPF1. And I'm going to type in network 172.30. I'll just do 0.0.0.255.255 area 0. And actually, before I do that, I'm going to copy and paste that to my clipboard, or copy it to my clipboard. I want to turn on a debug here because I want you to see the play action fake that happens. I'm going to just do a debug IP OSPF adjacency and, oh, of course, and the events, because I want to see both of those things in action when we watch the DR and BDR election. So I'm going to go up here and type in the network command, just paste it back in there, area 0, hit enter. Now, as soon as I do that, we should see the Ethernet 0 going up. That's good. We're building an LSA. We sent a hello. I'm expecting a little more to happen here. Okay, there we go. All right. No, stop. You all. I'll do you all so the hellos don't scroll us up. Look at this. Very similar to the other one, but a big chunk is in here with the DR BDR elections. You see right here that we have the, right after the hello is sent, we move into the two-way communication, which means the hellos have been exchanged and we are able to be neighbors because all the criteria match up. We move into a DR BDR election. Now right up front it says, hey, I'm going to elect the BDR as this and elect the DR as that. It knows right away because it says that the DR and the BDR are going to be based on the router ID. The priority has not been set at anything other than 1. I'll show you how to set that momentarily. But after that, after the DR and BDR are set up, everything else moves forward just as it continues in any other routers. The DVDs are sent. We send some link state requests to get some more information. The updates are sent back. Now, when you see some of these packets, duplicated, that's because I have 2 debugs that are turned on, the adjacencies and the events, some of which have overlapping information. So don't think that we're actually sending 2 packets every time we elect the DR and BDR. It's just the adjacencies and the events show duplicate information at times. Sometimes they show unique information between the 2. All right, let's go ahead and set up the last one, router 2. I'll get into global config mode, router OSPF, and let's do, you know what? Yeah, let's do 1. I keep having these great ideas, and I'm going to do that great idea as soon as we type this in. I'm going to type in network 172.30.0.0.0.255.255, area 0, which turns it on and will form neighbor relationships with everything else. Now, what I want you to see here is you can see the neighbor coming up. So we see the 2 neighbors on the Ethernet network have come up. I'm going to type in show IP OSPF neighbor. Now, as soon as I do that, you can see the neighbor relationships are at a full status, and we have the BDR and the DR that are elected. Now, let me hop over to router 3 real quick. I'm going to do a show IP OSPF neighbor, and you can see that it sees the DR and a DR other. That would be router 2 right here. Now, it's funny because I know I've looked at this a couple times, and I've thought, oh, well, where's the BDR in this picture? Well, if you don't see it in your neighbor list, chances are the BDR is you. Because remember, this is just a list of neighbors. So router 3 in this case must be the BDR because it's not listed in any of its neighbors. Now, what I want to show you is changing the router ID. Now, you saw, first off, that the router ID is the highest physical IP address on any given interface when the OSPF process starts. And we've seen that in action before our very eyes. When I type in show IP OSPF, on router 2, it says, hey, I am OSPF1 and I have this ID. That's my router ID because that's the highest active IP address on the interfaces when I started. Now, remember I also said loopback interfaces always beat physical. Let's test that theory. I'll type in interface loopback 10, just a random loopback interface, and type in IP address, and let's go low. Let's go real low. 1.0.0.1, right? As low as you can go. Oop, forgot a 5. There we go. I'll put a mask of all 255s, and that's common a lot on loopback interfaces to put a mask of all 255 so you don't actually kill the whole 1.0.0 network. Now, I'm going to go back here, and I'm going to type in show IP OSPF. Now, when you see this, you look at the ID, and you're like, well, it's the same thing. So did the loopback not overrule it? Well, here's the key. Once the router ID is chosen, it stays that way until the OSPF process is either restarted or the router is rebooted. So let's do that. I'm going to type in the command clear IP OSPF process. That's a way of wiping the OSPF process, restarting it without rebooting the whole router. Will ask me if I'm sure. Yes, I am. I should see the neighbors go down. There they go. They go down. And then very quickly, right after that, came back up because it just moved from loading to full. Now I'm going to type in show IP OSPF, and you can see, oh no, the router ID is still 172.30.50.2. Holy cow, let's check this out. I'm going to type in show IP interface brief. I'm totally surprised right now. Okay, we've got the loopback 10 interface. This is something I didn't expect to see. Let me, as simple as I can say it, let me try clearing that one more time. Clear IP OSPF process. Let me just make sure I'm not missing anything. Okay, process. Wipe that process one more time. Do a show IP OSPF. Look at that, 172.30.50.2. You know what? I am not convinced. I'm going to save my config and then reload the router. I'm going to pause the video while this router reloads because this is a 2500 series router. It's slow. But once the router reloads, I'll bring it back and we'll do the verification command again because I know that loopback interfaces beat the physical interfaces. So if this stays at 172.30.50.2 after a reload, then something is very, very wrong. So hang on, I'll pause the video, come back in a second. All right, the router's restarted, and I'm going to go ahead and hit enter here. Moment of truth. Let's get into privilege mode. I'm almost nervous to type this command. Show IP OSPF and hit enter. Ah, look at that. Okay. So, yikes. That scares me even more. I have never seen, I can tell you this right now, I have never seen a router have its OSPF process cleared and the router ID not change over to the loopback interface. I'll do the show IP interface brief just to prove that we still have this IP address on here under Ethernet 0, and it shows the lower loopback interface as the router ID, and that gives me enough ammo here to give you a grave warning that it is so essential to hard code your router ID. That craziness that we just saw right there where I created the loopback and cleared the process and there was no router ID that change that occurred, it didn't occur until I actually physically rebooted this router or did a reload of the router. When we get into the advanced configurations, my grave warning will make much more sense because knowing what the router ID is goes into some hard-coded configs. You're going to configure, like when I do a show IP OSPF neighbor, you're going to say, hey, for this router ID, for this neighbor ID, do this. And you're going to see some specific configs that relate directly to that ID. If the ID changes, your config breaks. Now, how often do you reload a Cisco router in a production world? Very rarely. I mean, it has to be a pretty major network update or event in order for the process to be reloaded. So, wow, that's interesting. I've never, because usually you clear the process. All right, enough on that. All right, so we've got the router ID, and that's set. Now, we've been allowing the election process to do its thing. And I've got to admit, while the router was reloading, I was going to Cisco's website and trying to back myself up. I was thinking, I know this is the way it is. And right there it says, is the highest IP address configured on the router is the router ID. But if a loopback is configured, that is the router ID. If there's multiple loopbacks, the highest loopback becomes the router ID. So if that didn't change, I was going to say, see, it's right there in the Cisco documentation. But it did. The point though is that it changes. It's dynamic and it changes around depending on what IP addresses you have configured. So what you'll want to do on every single router that's running OSPF is rather than leave the router ID election process to some random highest IP address scheme, you want to come under the routing process, under router OSPF, and type in router dash ID, followed by exactly what you want the router ID to be. Now that one beats everything. I'm going to put, in this case, 2.2.2.2. And notice, see, look at this. I told you. Reload or use the clear IP OSPF process. That's usually all it takes to change the router ID. But you can see the router ID is now going to be hard-coded as 2. And in lab environments, this is what I do all the time. I look at the router number, router 2, and I make that its router ID, 2.2.2.2. Now, if you want, you can create a loopback IP address on this router of 2.2.2.2 and then advertise that into the OSPF process by typing something like network 2.2.2.2.0.0.0.0 area 0, right? What that will do is make the router ID pingable because there's an actual interface behind it. However, if you do not create a loopback interface and you do not advertise that to the rest of the network, you cannot ping this IP address. It's just the router's name. I've never really seen an advantage to advertising router IDs to the rest of the domain, but it's up to you if you want to. So at this point, I'm going to type in show IP OSPF because I got to see it again. There's our 10.1.0.0. I'm going to type in clear IP OSPF process. Whoops. Hit yes to reset it, and I'll do the show again. Look at that. Can we say consistent inconsistency there? I have a witness. This has been videotaped. I'm going to ship this off to Cisco and say, your router is crazy. Because didn't you see that? It changed now that I cleared the process, but it didn't change before. Huh. You saw it here first, folks. All right. So with that in mind, what am I talking about? Okay, I was going to do the show IP OSPF neighbors. Right now, the DR is still 50.4 and the BDR is still 50.3. Now, that is being decided because they have the higher router IDs. Now we're not even in the competition, right? The last thing I want to show you, at least on the base configuration of OSPF, is how to influence the election without changing router IDs. What you can do, I'm going to type in there's no do command here. I'm going to do a show IP interface brief. You can see that Ethernet 0 is the interface that router 2 is connected to the rest of the network with. So I'm going to hop back over here and go under that interface because remember the DR and BDR is on a per interface basis. It's not like there's one DR that's elected for the whole network. So router 1 will be a DR for this shared Ethernet segment, and then we have a big election that happens here for this Ethernet segment. The way we can influence it is by going under the interface that the router is using to reach the shared segment and type in the command IP OSPF followed by priority. See that one in the list? That is the one that is transmitted in the hello packet, and we'll change the priority from something from 0 to 255 where higher is better. Now by default, I mentioned that the priorities for all the routers, they're all 0. Or I'm sorry, they're all 1. So they're all tied by default. You can make them 0, and at that point, the router says, I will never become a DR or BDR. Putting the priority down to 0 completely exempts it from the election process and says, I will not participate in this. But anything above 0 says this is a valid election ballot, and all I have to do is set it to something higher than everything else has, in this case a 2, and we should see router 2 take over as the DR of the network. Now I may have to clear the process, or who knows, reload the router. I hope not, but let's do a show IP OSPF neighbor. As of right now, it's still the BDR and DR being 50.3 and 4, so I'm going to do a clear IP OSPF process. and hit yes to that. Bring the neighbors down and back up. Let's do a show IP OSPF neighbor. You know what I'm gonna do? I'm gonna come over to router 3 and clear the process, because a lot of times once something is elected as the DR and BDR, and I'm also gonna jump over to router 4 and do a clear IP OSPF process. Um, Once they're elected, it does not exempt, meaning there's not like a coup that can take place and other routers take over. Now let's come back to router 2, do a show IP OSPF neighbor as after I've cleared it on those two other neighbors. There we go. You see what happened? At that point, router 2 became the DR. The way we can notice that is because I don't see a DR in the list. From router 2's perspective, the neighbor 50.3 is a DR other, and this neighbor, which is currently in X start state, meaning it's having some problems getting started. I may need to clear the process on one end or the other. You know, all this clearing is probably just throwing OSPF into chaos. But once it does come back and become a full neighbor, what's going to happen is the 50.4 becomes the BDR, because after the priority of 2, which router 2 has, router 4 is the next one in the election, because these are both priority 1, so it's going to use the router ID to break the tie, and that one has the highest IP address of 3 and 4. So router 2 will now become, there we go, and you can see both neighbors went to full. Router, you know what? I'm done. That's it. I'm done. I think router 2 has issues because you can see right here DR other and BDR, and I just did the show neighbor and now it's gone back to what it was. At that point, I will say router 2 is insane, but you see the concept, right? You see the concept that the priority influence the election. You influence the election by adjusting the priority up, or you exempt a router from the election by just using a priority of 0. All right. With that being said, I think I've shown all of the verification commands as we've gone through, but I do want to make sure I hit all of them. We do a show IP OSPF neighbor. That's, in my opinion, one of the handiest commands. But show IP OSPF neighbor, very handy. Show IP OSPF interface is handy to see primarily the timers that are being used. And when we get into the more advanced topologies, you'll find that knowing the timers is one of the huge things that goes into your troubleshooting. Show IP OSPF. Let's see what other big ones are there. I'll say this one is valid, but I wouldn't say it's a big one. I'm going to type in show IP OSPF database. Now, some people would argue with me on that. The database shows the topology, everything that OSPF knows about. However, it's just not in a fashion that's very user-friendly until we get into a multi-area environment. What this does is show all the neighbors that exist in the OSPF area. You can see the routers in area 0. So it even knows about, look at this, it even knows about 49.1. So router 2, even though it's not connected to router 1, it still knows that that exists in the table, or in the topology table. And you can see right here, they have these sequence numbers. These are the sequence numbers that's used between the neighbors. Every single neighbor uses a sequence number to say, this is my latest and greatest copy of the database. Anytime there's a change, anytime there's a periodic update, which happens once every 30 minutes for OSPF, the sequence number goes up by 1. It's a 4-byte value and goes from 8000000 all the way to 8FFFFFFF. So if your router is running for long enough, you can see it, these things don't change often, once every 30 minutes. If your router's running for long enough, eventually that sequence number will reach all Fs, and OSPF uses a special process to notify the neighbors and then cycle back to 80000 and start the whole process again. But this is a quick way that you can verify that the neighbors are synchronized. You should always have the same sequence number between any two set of neighbors, and you can also check the age of the database, the age of the topology table as it appears from each neighbor. That is in seconds. So the last major update that was received from this neighbor, which is router 4, was 169 seconds ago. And that age will continue to increase until we hit the next periodic update 30 minutes later, and then the age will drop back down to 0. So that's a view of the database. Again, once we get into a multi-area environment, that will start making a lot more sense. Now, before we wrap things up, I have one more thing to say. and my curiosity ate away at me as I paused the video between the last show command and the summary, and I just reloaded all the routers in that little pod of routers that we were having the weird things going on. And look. Once they came back up, I just reloaded every single router. As it came back up, you can see the negotiation happen. It's two-way, and then eventually, wham! It goes from loading to full. And now router 2.2.2.2 as its router ID has become the DR. Router 3 over there is considered the DR other. So I'm just thinking with all the chaos and my poor little 2500 series router 2 just couldn't handle all the stuff I was doing, clearing the processes of all the routers. So let's wrap things up. First thing that we did was get OSPF working, and that was just using the network command. We can use the network command as a gauge or as a method to enable interfaces to run OSPF. Oh, and you know what? By the way, I do want to show you, this is a summary slide. What am I doing? Adding new stuff? Yes. I want to show you something. I'm going to take you to one of the brand new routers Cisco had. This is actually an integrated service router, 2800 series. We enable OSPF with the network command, right? Look at a way that they've added in new routers. Now, the network command is still there. You can still use it, so it's not like it's gone away. But the network command really just tells what interfaces should run OSPF, right? So they've actually added a feature to the interface level commands where I can type in IP OSPF under the interface, and look at this. This wasn't in the help menu of the other routers. I have a process ID. I can actually go in there and say IP OSPF process 1 and then type in what area it is, and I'll put area, area 0 and hit enter if I want to include secondary IP addresses and so on. But rather than use the network command, I can just go under the interface that I want to run OSPF on, type that command in what area it belongs in, and wham! Just like that, it's going to start running OSPF. No necessary wildcard mask, no looking at the IP address. You enable it on the interface. I think that's going to be such a better method as all the new routers start, taking over the world and all of the older ones get out of the way. By the way, when we get to IP version 6, OSPF for version 6 has been implemented on Cisco routers that there is no network command. As in, that way I just showed you is the only way that you can get OSPF working. They've removed the network command. So, a lot of things changing, huh? So, on the summary, there it is, getting OSPF working, adding a little bit more to it to expand on what's coming in the future. We saw the router ID changing the name of the router and the priority commands to influence the DR and BDR election. And then, as promised, spliced all the way through was the debug commands, clearing the process, verifying that whole thing with the various show commands I demonstrated for you. I hope this has been informative for you, and I'd like to thank you for viewing.